Okay, so we finished the last lecture in the middle of the following argument. We had seen that a characteristically simple group, so a group which has no, non-trivial group which has no characteristic subgroups beside the two obvious one and the whole group, I mean a finite one, is a product of isomorphic simple groups. So one case is when M is abelian, then these simple groups have to be abelian and then are cyclic of order P. And we treated that separately. And then we have the case when these factors are isomorphic, non-abelian simple groups. And I wanted to prove that such a product is in fact characteristically simple, because I proved if it's characteristically simple, then it's a product of this form, but we need to prove the converse. So the first thing I proved is I took L to be a normal subgroup of M, different from 1, and I showed with an argument, I went through this argument last time, that if in L there is an element whose first component is different from 1, I mean, L is different from 1, so one of the components, there will be an element with one of the components different from 1. I'll take the first one, but it might be the ith component, I am not sure. And then by choosing an argument which is not in the center, this is not abelian, so the center is trivial, we found essentially that we found that in this normal subgroup, which is L, okay, fine, yes, there is an element which has all the components equal to 1 except the first one, which is non-trivial, okay? And since this is normal and S1 is simple, it turns out that S1 is containing L. So what we have proved, if there is a normal subgroup L of M, which is different from 1, then L contains one of the SI, okay? Because I mean, I have taken 1 just for simplicity, but really I can only say that it contains one of the SI. As I mentioned last time, this shows that the SI, these factors, are the unique minimal normal subgroups of M, and this is the part of the so-called Krull-Schmidt theory, which is one of the seminars that I mentioned. Good, and so we are nearly finished because so far we have been discussing a normal subgroup L of M, okay, M which is of this form. And then, I mean, this M is supposed to be, we want to prove that it's characteristically simple. It means it has no characteristic subgroup besides the two obvious ones. It might have, it will have normal subgroups. And now we say, what if L is now characteristic in M? Want to prove that, okay, the L equals M, okay? L is different from 1, so it has to be M. And I know that L contains SI. And this depends from a fact that is relatively elementary. You probably saw it already, but let's go through it again quickly. Suppose you have, suppose omega and delta are sets. I normally do this argument in theory regrouping, but let me repeat it. And let delta to the omega, this should be a standard notation, the set of maps from omega to delta, okay? And yes, suppose the group, let G be a group acting on omega, okay? So domain of these functions. Then G acts on delta to the omega by, so you have f in a function from omega to delta. So what's f and g in G? So what is f to the g? So my actions are right actions. Some of you will have taken algebra, the algebra course in Willem de Graaf. He uses left actions. My action are left action. So what is the value of okay, so I take f, I take its image, which has to be defined under an element g on G. What is its value on x, x being an element on omega? And this will be f x G inverse, okay? Because by assumption G acts on omega, so this is the action of x of omega of G inverse. And it's an immediate fact that you need to take this inverse because you want this to be a right action. So let's do the quick calculation. What happens if I first apply G and then H to F? I want to show that this equals FGH, okay? This is to be proved. So so let's, for every X. So I take this on X. So what's this? Is this function under H on X. So it's this function, H inverse, okay? Because this is the action. And then G acts on this. So this is F X H inverse, G inverse, okay? But this is nothing else but by the usual properties of the inverse of X GH inverse. And this is exactly the definition of F GH X, okay? So you see that you need this inverse, otherwise if you don't take the inverse, this is a left action. Nothing wrong with left action, but I'm dealing with the right actions. Okay, so why is this important? Because if you take S1, let me check my notation. FK, okay, SK. If you take M, which is S1, S2, SK, this product is nothing else that the set S, so all these I are isomorphic to S, the set of maps from 1 to K to S, okay? Because the elements here are n tuples, like this, where xi are in S. After all, these are all isomorphic to S, and of course this is just a way of writing a function from 1 to K to S. Okay, so you may think that xi is nothing else than the value of x on I, where x is a function here. Okay, so K tuples are just functions from 1 to K S, and then of course the group, the symmetric group SK, sorry, oh no, this is audible, sorry. Yes, okay, let's call sim K acts naturally. By definition is the group of permutation on 1K, so my notation is horrible. And then it acts on this, so on M equal S1 SK. And what does it do? Well, an element of sim K, of the symmetric group, permutes the K, the I's, so it permutes the components, okay, by computing, by permuting the components Si. So if L, which was this, let's go to the next page. So if the characteristic, yes, I should add something, and this action, it's easy to verify, and this is an action by automorphisms. So these maps are automorphisms of N. Okay, this is to verify. This action which permutes the component, permutes the xi between among themselves. And so if the characteristic subgroup L contains the component Si, by applying these automorphisms, we see that L contains all the S1, S2, Sk, because these automorphisms that we have just built permute the components. And so if you have Si, you have any of the others. And so it follows that L is the whole of M. Okay? So this proves that such a product of isomorphic simple groups, this M equal S1, Sk, with all Si isomorphic to S, this non-abelian simple, is characteristically simple, okay? And remember, this is when these factors are non-abelian. When these are abelian, this is different. There is a different argument which involves the general linear group. Because, I mean, at some point I made the critical assumption that Si is non-abelian simple. That is, in particular, I use the fact that the center is trivial. Okay, so we need a different argument when these are abelian. Good, and so this settles this. We studied, recall that we studied these characteristically simple subgroups because these are the factors of a normal series. We'll get back with this when we discuss soluble groups are of this form. And now, before getting to soluble groups, we want to consider the questions of uniqueness of an omega composition series. Let's start with an example to see that such uniqueness cannot be taken literally. Why is it so? Because if you consider G a group, okay, let's say generated by G, cyclic of order 6, okay? It has G, okay, it has exactly two composition series. So a composition series means just a series that each term normals in the next, but this is abelian, so this is really also a normal series. So this is what I call a principal series, but it is not important. So the first one, well, there's no first one really, is given by, okay, all subgroups are normal because this is cyclic and abelian, is the following, for instance. And the second one is this. So I think whether we should know quite well if G has order 6, I mean little g, then G cube has order 2. So let's write this. This is the order of the subgroup, and the index is 3. And G squared is order 3, and index 2. Okay? So these are two different composition series, also principal series. So you cannot expect uniqueness term by term, but what you can prove is the following. Let's call it a theorem. Let G be a finite, let's say, omega group. And we'll see in the proof why dealing with omega groups, it's a simple concept, but it's useful in this case. Suppose G, if it's finite, then it has two omega composition series, then up to a permutation. The factors of two omega composition series of G are pairwise isomorphic. Once you have had time to write this down, I'll go back to the previous slide, to the previous board, because this is what happens here, okay? So let's consider the factors here. This factor is order 2, cyclic of order 2. This factor is order 3, cyclic of order 3. Here, this factor is order 3, so cyclic of order 3. And this factor is cyclic of order 2. So they are isomorphic, but after a permutation. So this is isomorphic to this is isomorphic to this, okay? So it's not that these two are isomorphic and these two are isomorphic. So this is what I mean by up to a permutation, okay? And let's see how this theorem develops. Perhaps I'll give you an exercise. I should remember to add it because I don't think it was in the sheets I handed out 2 years ago. Suppose a G is cyclic of order P1, P2, Pk, where the Pi are distinct primes, okay? Then G has k factorial, this different, let's say composition series, okay? With factors up to a permutation of order P1, P2, Pk. So what I mean here, since this is cyclic, the factor have to be simple groups. So these are simple abelian groups, and so are cyclic of order P. What I'm saying here, that you can find the composition series which realize all permutations of this Pi, okay? So for instance, this is a special case because here G is order 6, so it's a product of just 2 primes, and you see you have two composition series. But if you have K, then you have K factorial, because you can permute, put the primes in the order you want by taking the suitable powers, okay? Okay, so let's prove this. And this is useful. This is interesting because it shows, as I said, why omega groups are a convenient objects to consider. And okay, so proof. Okay, so consider 2 omega composition series of G. So consider, oh yes, I should have added something. So this starts with H naught and so on. This gets to Hn minus 1 and then to Hn equal to G. And the other is, let's call it K naught, K1, Km minus 1. This is something I forget to say in the statement. Let's go back. I cannot exclude in principle that the 2 composition series have different lengths. So let's go back to this. Then the 2 series have the same length. And okay, so I've added this because otherwise I cannot speak of a permutation. The 2 series have the same length, so the same number of factors in particular, and then the factors of the series are pairwise isomorphic under a permutation, which now makes sense because it's not that you have, say, 2 factors in one series and 7 in the others, and then what's the permutation, okay? So let's see how it works. So remember that actually I put this equal here, but by definition in a series all terms are distinct, okay? This is just the definition of any series. If Hn minus 1 is equal to Kn minus 1, Okay, okay. So we argue by induction on, well, let's say the order of G, okay? Or I could add an induction on the length of one of the two series, but since these are, yes, finite groups, right? Yes, finite groups, I can argue on induction, by induction. So if this holds, note that since the terms are distinct, these two groups, since hn minus 1, the order, which in this case is equal, okay, just because I assume this, is less than the order of G, okay, by induction, the assumption holds. This is the critical point for the omega series 1 equal h naught h1 until hn minus 1 and 1 equals k naught k1 kn minus 1. And this is an important point. No, this is, let me think. Yes, okay, fine. So these groups are smaller than G, than the order of G. And so what I can say, this means then the length is the same. And so this implies in particular, of course, that n equals m. And the factors here are isomorphic up to a permutation. Okay, so the factor of these two series, okay? Here means here. And then there's something missing, but the remaining factor is the same. It's the same. Because I'm assuming here that the hn minus 1 equals kn minus 1, and this is this one, which is literally equal to this one. Okay, and so we prove this. There is the top factor is the same for the two series, and by induction I restrict to this, and the factors also are permuted, and it has the same length. Okay, so this is the case when these two terms are the same. Perhaps I'll copy this to the next slide, to the next whatever. Okay. Add to new page. Great. Let's try and move it. Yes, okay, I'll move it here. Okay, so this time I assume that, assume now that hn minus 1 is different from kn minus 1. Okay, and consider the intersection, which is an omega subgroup. Okay, because I mean the intersection of two omega subgroups is an omega subgroup. Being an omega subgroup means being invariant under the action of the element of omega. So I mean, if this is invariant, this is invariant. An element here has to be here, and under the action of omega has to be both here and here. So the intersection. Okay, so the situation is the following: you have 1, and you have L here. Okay. And then L is the intersection of hn minus 1. And then you go to G, and this is here you have k minus 1. Okay. Now the point is that just a second. Yes. Okay. So let's consider what happens here in this square or something. Okay. First, note that since these two are distinct, hn minus 1, kn minus 1 cannot be equal hn minus 1 or kn minus 1 because they are distinct. Okay. So this is strictly greater, no, I should write this on the other side, well, anyway, than Hn minus 1, okay? Because Kn minus 1 is distinct, in particular, is not contained here. But remember, this is an omega composition series, and this is an omega subgroup, which is contained in G, okay? Again, because it's a product of two omega subgroups. It's a subgroup because they are both normal in G, okay? And but by definition, this is a composition series, an omega composition series. It means that between G and Hn minus 1, between any two consecutive terms, there are no more omega subgroups. So this is an omega subgroup comprised between the two. It doesn't coincide with the first one, with this, so it has to be this one, okay? Since, so by this argument, then this product has to be the same as G, okay? But then look at this configuration, okay? Okay, what's this factor here? Okay, so let's look at this factor here. This factor here is G over Hn minus 1, okay, which is by this factor Hn minus 1 Kn minus 1 over Hn minus 1, okay? But by the second isomorphism theorem for groups, such quotient is isomorphic to, well, you simplify Hn minus 1, so you get Kn minus 1 here, but here you have to keep the intersection of the two. And this is exactly what I called L, okay? So what I've shown using the second isomorphism theorem is that this one is isomorphic to this one, because this is the quotient group of Kn minus 1 over L. With the same argument, you prove that this is isomorphic to this. Okay, it's the same argument. That is, you do this, and you prove that this is isomorphic to Hn minus 1 over L. Okay, so you see where the permutations are coming in, because this is a two-cycle, say, like the case 3 and 2, okay? Because this is isomorphic to this, and this is isomorphic to this. So they are not isomorphic directly, but you have to exchange them. Here, starting the permutations. And now the point is the following. Let's look at the factors of the first series, okay? Let's call it A and let's call it B. So the factors, no, okay, let's put it like this, okay? Consider a composition series of L. So this will be something like L naught, L1, and so on until whatever, L, I don't know, T, which is equal to L. Okay, this is a these groups are finite, so they have a composition series. And here there is an important point, okay? Because L is an omega group, so it has a finite omega group, so it has an omega composition series. If you don't consider this omega concept, suppose, for instance, you are talking about normal series. What does it mean? So suppose that the two series are series in which not only each subgroup is normal in the next, but each subgroup is normal in G, okay? So you proceed by induction, L is smaller, okay, whatever. You take L, which is smaller. So it will have a normal series. But if you argue like this, you can only say that these Li are normal in L, not in G, okay? So the concept of omega series allows you to avoid this difficulty by saying it doesn't matter whether I take G or a subgroup or even a smaller subgroup. What's acting on every subgroup is this omega, which is in the case, for instance, of principal series is the inner automorphism of G. So the omega acting is fixed. In the case of a principal series, it will be in G. the inner automorphism of G, not of L or Hn minus 1 or Kn minus 1. So even if I move to L, these subgroups will be omega subgroups. So when omega is in G, these subgroups will be normal in G. Okay. So the idea is you consider not just normal series of L, but a series which subgroups are normal in G. But with this omega concept, you avoid this difficulty. Except, I mean, you need to be aware that that this is solving a, let's say that this omega concept solves a problem you didn't know you had. Okay. Okay, so consider an omega composition series of L. Okay, and then this is slightly cumbersome to write. On Hn minus 1, no, I'll write it down. On Hn minus 1, you have two omega composition series. One is this one, okay? And the other is this one. Oh, I could have used another color. Let's use another color because this is just being also. Let's take green. So I have this series, okay, on Hn minus 1, I mean. So let's erase this. And I have this one, okay? So by the induction hypothesis, since Hn minus 1 is smaller, these two series have the same length and have isomorphic composition series up to a permutation. Then I have, if I consider Kn minus 1, it has two composition series, one of this one, and the other one is this one. Okay, so this and this. No, sorry, again, once more I went too far. So this and this have the same length and have the same composition factors up to a permutation. But then you see, this shows that if you want now to go to G, you have the permutation, the factor groups of this plus this factor, G over Hn minus 1, okay, which are the same of this series plus the same factor. And now consider this series, the K series. The composition factors are the factors of Kn minus 1 plus G over Kn minus 1, okay, which are the same as this. And these are the same of this other series, the series going up and the series going down. So these factors are in common. These two are not the same, but then they are isomorphic to this, as we saw. So if you combine all this, you'll find that the composition, the factor of A and the factor of B are the same up to a permutation, okay? Because as I say, they are the same of this series plus this, and these are the same as this series plus this, and okay, and here you have just this exchange. Perhaps I should mention that the proof by induction really shows you how these permutations are coming in, because here I have a 2-cycle, okay? So if I look at this red thing, I'm exchanging just two factors, okay? If you repeat, induction means, it's a practical way of avoiding to say that repeat the argument for early and so on, you'll have a product of 2 cycles and then an arbitrary permutation. I hope this is clear. I didn't really wrote everything down, but I mean, you compare A with say A prime, what goes on top. No, let's use a different color. Let's use black, please. A prime, A with A prime, B with B prime, and then this exchange shows that the composition factors are the same, okay? And this is an important fact, I mean, this uniqueness of up to permutations. Okay, so, I mean, you cannot have literal uniqueness term by term, but up to a permutation. And that's about what I wanted to say on these compositions and the like, although they will pop up again once we speak of soluble groups. So let's start speaking about soluble groups. Yes, I'll consider a general case, but then we'll stick to finite soluble groups. as I said, the reason I give this introduction to soluble groups is that one of the main results we will have is the Burnside PAQB theorem that tells that finite groups whose order is divisible, whose order is divisible by only at most 2 primes are soluble. Okay, so let's recall soluble groups. Let's recall first some basic definitions. The first definition of a commutator, okay? And so the idea in general in a group for A, B, in G in general, you will have that AB is different from BA. What it means in general is that, well, there will be pairs of elements commuting, but if the group is non-abelian, by definition, there will be pairs like this. So the commutator, this is the commutator of A and B, is an element that measures the difference between these 2 factors. And there are 2 possible definitions. Well, I'll write down one and comment on the other. You see, this is the inverse of this times this, okay? So it will be obvious, but I write it down, that when these 2 are equal, okay, BA equals AB, then this will be 1. This is one of the reasons called commutator. So what's this? It is A inverse, B inverse, AB, okay? There is another possible definition in which you take AB times BA inverse, okay? But I use this one, where you start with the inverses. The other definition starts with AB and then A inverse, B inverse, okay? So it's immediate from this, okay, that lemma, in this situation, the following are equivalent. For A and B in a group G, AB equals BA, and the commutator is 1. Okay? And okay, so that's it. Exercise, I leave you as an exercise which is immediate by this, is that inverse of a commutator is again a commutator. Okay, there is perhaps an important thing that I will say before going on. Yes, so if you consider, recall that the conjugate of A by B is conjugate. It has already appeared in the proof that the product of isomorphic simple non-abelian groups is characteristically simple. This conjugate, this is B inverse A B, and as you see, it's this part here, that's an A inverse here. So you multiply here by this, and you obtain that is of this form. So this tells you, so far this is totally elementary, that if you conjugate A by B, you obtain A, but there is a correcting factor, the commutator, okay? And recall that, of course, N, a subgroup of G, is normal if for A in N and B in G, for all A in N and B in G, you have A to the B in N. But since A to the B is equal to this and this is an N, this is a product of 2 factors. So if A and A to the B are in N, this means that the commutator is in N, and conversely. And so this is equivalent if and only if, okay, if the commutator is in N, okay, for all of this. This should be clear because, you have A which is in N anyway, okay? So if this is in N, then the commutator is in N because it's a product of A inverse but times A to the B. If the commutator is in N, this is a product of 2 elements of N, so this is N. And so this fact that I will repeat in a second in a different context is a very usable way for stating that the group that the subgroup is normal. Okay, instead of using conjugates, you can use commutators. That's the way I normally do it in my work. Okay, so let's give some more definition. Okay, let G be a group. And there is a subgroup which is traditionally denoted by G prime, which is the subgroup generated by all the commutators. Okay, it's called the derived subgroup, derived or commutator. Well, commutator is obvious, derived or less. So the derived subgroup of N, of G. Okay. Perhaps I should mention it's in the notes. In general, so this is a group generated by the commutators. In general, G prime won't consist only of commutators, but it has been proved in 2010, so it's a very recent fact, that there is the article is mentioned in the notes, that if G is a finite simple group, okay, let's put it here. If G is a finite simple group, then G prime, which in principle is just generated, it means not all elements here are commutators. G prime is indeed the set of commutators. Finite simple, yes, okay, fine. And this is one of the instances of application of the classification of finite simple groups. Essentially, one goes in a reasonable way through the list of finite simple groups, since this is available. Okay, there are a few exercises. Okay, let's state a couple of exercises that you'll find in the notes. You can prove, now I can use safely Sn for the symmetric group. So the derived subgroup of the symmetric group is the alternating group, okay, for n greater than or equal to 2. And also an prime equals to n for n, but here you need n to be at least 5, okay? There are some hints on how you do it in the notes. Good. So I have defined the derived subgroup. More generally, okay, if A and B are subgroups of G, define their mutual commutator as you write it like this. So it's a general, okay, fine, okay, as the span of A of the subgroup generated by the commutators where you take the first element in A and the second element in B, okay? So this can also be written as GG, okay? Because it's an instance when A and B coincide and are the elements of G.